Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week we are covering the revision of fluid mechanics, okay, and we have already covered fluid statics, okay, and in the later half of this week we are covering fluid dynamics, okay, and this would be the last, final and concluding lecture for fluid dynamics as well. In the previous lecture, we looked into some of the applications of Bernoulli's principle, and in this lecture also, we are going to look some more examples for the application of Bernoulli's principle. Okay, so without losing any further time, let's share our screen. So here we go. So before starting, let's again have a look at the Bernoulli's principle statement. Okay, so as you know, that Bernoulli's principle is applicable for an ideal fluid. Ideal fluid, for example, you can say it would be incompressible, homogeneous, non-viscous. It is applicable for an ideal fluid of these natures, okay, for a laminar flow. And the statement is, like, during the flow, P plus rho GH plus half rho V square is going to be a constant, where again P is the pressure energy per unit volume, rho GH is gravitational potential energy per unit volume, and half rho V square is kinetic energy per unit volume of the liquid over here. Okay, so in yesterday's class we looked at several of its applications. Okay, and today's class we are going to look more into that. So the first example here I am going to take is the example of perfume atomizer. Okay, you all might have seen it and used it. Okay, and one simple model we will be taking for our discussion. So the thing is, a perfume atomizer looks something like this. So there is a bulb, okay, and there is a tube attached with it, okay, from where the perfume is sprayed, and this perfume container is attached to the neck of this tube, okay, and somewhere here you keep some perfume. Okay, so what is the working principle over here for a perfume atomizer? That you press this bulb with some, let's say, extra pressure delta P. Okay, you press this bulb. So what happens, that air starts flowing through this tube. Okay, so once air starts flowing through the tube here, for example, the velocity of air will be more, so that will cause the pressure to decrease at this point. Okay, so if there is decrease in pressure at this point, that will cause the liquid to rise in this column over here, and when this liquid will be risen at that point, the air will strike to the liquid and it will convert it into little droplets, and those droplets will come out from this opening. So you can say this liquid will be sprayed. Okay, and that is the working principle of perfume atomizer. Okay, we have discussed this, we have explained it analytically, and now it's our job to explain it qualitatively as well. Okay, so let's look into the equations. Okay, so here let's say the problem statement is, let's say, for example, if this height, okay, the height of the open surface of the perfume from the from this point over here, from the tube, is, let's say, equal to H. Okay, and delta P is the extra pressure we are imposing, and let's say the density of air is rho air and the density of the liquid is rho liquid. Okay, so we are interested in finding out that what should be this velocity V, or the minimum velocity of air, okay, in order to lift this liquid to this level over here such that it is sprayed, okay, afterwards. So the question here is, what would be the minimum velocity of air for the perfume to lift in the tube of the sprayer over here? Okay, so how are we going to deal with this? So now you must understand, like, if the liquid is uh, liquid is lift in this level, okay, now you must realize, so we need to write the Bernoulli's principle for air as well as the liquid also. So let's use one color pen and let's define different points. Let's say define one point inside this bulb, let's say P1, point 1, and let's define 1.2 here. And in this liquid, okay, let's define two other points. Let's say the liquid has risen till here, okay, and this is point 3 and this here is point 4. Let's say this here is point 4. Okay, so what we are going to do is we are going to apply Bernoulli's principle for point 1 and 2, and that will be in air, and we will be applying Bernoulli's principle for point 3 and 4, which will be in liquid. Okay, so let's try to do that one by one. So in air, when we are writing Bernoulli's principle, we must realize the expression P1 plus rho g H1 plus half rho V1 square is equal to P2 plus rho g H2 plus half rho V2 square. Okay, so this is the original statement for Bernoulli's principle. Now, first of all, you have to realize that this point 1 and point 2 are at the same height, so there will be, these two terms will be cancelling each other. And another thing you have to realize, since we are working with air as fluid, this density term will be nothing but the density of air. Okay, this is nothing but density of air. Okay, and now we wish to find write the expression for P1, P2, etc. And also you must realize that the velocity of air inside this bulb, the air inside this bulb over here will be almost stationary, so this term will be approximately equal to 0. So now this equation turns out to be equal to P1 is equal to P2 plus half rho air into V2 square. Now you must realize, first of all, like the gauge pressure, like let's work in terms of gauge pressure. In the previous class only, we discussed that whenever we are interested in pressure difference, like here we are interested in P1 minus P2 or P2 minus P1, etc. So we can work in terms of gauge pressure because the atmospheric pressure term will cancel both sides. Okay, so it would be more convenient for us to work in terms of gauge pressure. So gauge pressure at point 1, see, the pressure has been raised by delta P. So the gauge pressure at point 1 would be delta P. Obviously, you must understand that the absolute pressure at point 1 will be nothing but P ATM plus delta P. In that case, let's say the gauge pressure at point 2 is P2 plus again the same expression rho air into V2 square. So this gives us like P2 is equal to, that is nothing but delta P minus half rho air into V2 square. Okay, so this is one of the expression that we have used Bernoulli's principle in air. And let's have another equation for Bernoulli's principle whenever we are writing between point 3 and 4, that will be in liquid. Okay, so let's write that equation. in liquid. Let's write the Bernoulli's principle between point 3 and 4. So what we will be writing here is P3 plus rho GH3 plus half rho V3 square must be equal to P4 plus rho GH4 plus half rho V4 square. Okay, so these terms. Okay, now you see. So let's look at the terms one by one over here. So P3, P3 here, the pressure P3, gauge pressure we are looking at, and let's say this is the reference level. So you can say H4 is equal to 0 and H3 you can write it as H. So rho G H3 would be nothing but, and rho here must be rho L. So rho L G H you must write, and plus half rho V3 square you can write, and P4, the pressure at this point, this is at the open surface of the liquid, so obviously the pressure here is going to be atmospheric pressure. So the gauge pressure at point 4 is going to be equal to 0. H4 is equal to 0 at this point, so that will be 0 as well. And this point here, this point, since its cross-sectional area of this surface over here, you can assume to be much less than the cross-sectional area of this tube over here. So this term V4 would be very negligible. Okay, so that term you can approximate it equal to 0. So in that case, the value of P3 we have got, and P3 is equal to nothing but minus rho LGH minus half rho V3 square. So don't worry about this negative sign, because here P3 we have written it as gauge pressure, and this simply means that the pressure is less by this much amount from the atmospheric pressure. It does not suggest that the pressure at point 3 is negative, only the gauge pressure is negative. So that means it is that much less from the atmospheric pressure. And now you must realize this point 3 is exposed to point 2. So what we can say over here, that the pressure at like P2 will be equal to P3. So when we will be writing this expression, P2 is nothing but delta P minus half rho A V2 square you can say, and that is equal to minus rho LGH minus half rho rho liquid, that was rho liquid into V3 square. So now rearranging, what we will be getting it as half rho A V2 square is equal to delta P plus rho LGH plus half rho L V3 square. So now it has been asked to us that what would be the minimum speed V2, what would be the minimum value of V2 to just raise the liquid in this tube. So for that case, in order to have minimum value of V2, like we can put the value of V3, value of V2 would be minimum when value of V3 is 0. So this term, let's put it at equal to 0. So this will simply give us like V2 will be equal to 2 times delta P plus rho LGH divided by rho A and the root under of this quantity. So this V2 is nothing but the minimum speed of the air, okay, which will be able to lift the liquid in the sprayer tube, and then later on it will be sprayed also. So this was one concept of the perfume atomizer. And let's extend this discussion, and let's take one example, such similar kind of example based on similar working principle. Okay, and that is the example of, you can say, the sprayer. Okay, and this question, this interesting question, was asked in JEE Advanced 2014. So let's look at that problem, and that is the problem of a sprayer gun, the one like the one you used in Holi in order to spray color over other people. Okay, so this is how the structure look like. Some simple model of sprayer gun is what we are having, is a tube. Okay, and at the neck, the cross-sectional area of the tube is kept less, and near the opening of this neck, okay, we put a small container in which some color is, you fill some color here. Okay, and there is a piston attached to it. Okay, which you push. Okay, so when you push it from here, the piston will be moving in this direction. Okay, and this piston will be moving, so uh, that will push the air inside. This is sprayer, air inside this tube. Okay, and now in the previous example of the atomizer, the basic objective was to somehow lower the pressure at this point, okay, such that this lowered pressure will create a pressure difference and liquid will be lifted up to this level, and later on the pushing air will push the liquid as well, and liquid will be sprayed from this region over here. Okay, so the question that was being asked, like, if for a given constant speed of the piston, let's say the speed of the piston is v1. Okay, for a given piston speed, the question that was being asked was that if the density of air is rho A and the density of the liquid is rho L, then for a given piston speed, the volumetric flow rate at which the liquid is sprayed will be proportional to the volumetric flow rate of the liquid will be proportional to what quantity. So let's try to find out the exact expression for the volumetric flow rate of the liquid over here. So let's define some cross-sectional area on our own. So let's say this cross-sectional area here is A1, and this cross-sectional area here is A2, and let's say this cross-sectional area here is A3, etc. And we wish to find out the volumetric flow rate of the liquid for a given constant speed V1 of the piston. And now you must realize, first of all, okay, you can apply principle of continuity between this cross section here and this cross section here for the air, and that will be A1 V1 is equal to A2 V2 over here. So V2, we are simply getting it as A1 by A2 into V1 over here. So now you should realize that A1 is quite large in comparison to A2. So this quantity here is large. So V2 is like large in comparison to V1. Clearly you can see. So that is what we have done. Like, we have increased the velocity over here. So at the cost of increased velocity, the pressure would be decreasing at this point. So now can we write the gauge pressure at this point over here? Let's name the point as well. Okay, so let's say this is point 1. Let's use some other color pen. This is point 1 and this here is point 2. So let's let's write the Bernoulli's principle in this between point 1 and 2. So here you can say, like, here the air would be, let's say, nearly at atmospheric pressure. So let's say P1, let's write the equation again. So P1 plus rho g h1 term and rho g h2 term left hand side and right hand side will get cancelled, because these two cross sectional areas are at the same level, you can see. So P1 simply we will write, and we will be writing half uh, rho air into V1 square, that will be equal to P2, okay, plus half rho air into V2 square. Okay, And now you must realize, like, P2 here can be written as, P2 here can be written as, or first of all, P1 here, since the pressure here would be nearly atmospheric pressure, so that would be 0 plus simply half rho A V1 square, and P2 plus half rho A V2 square. And rearranging this equation, P2 we will be getting it as like half rho A uh, into, you can say, that will be V1 square minus V2 square. Okay, and we wish to write this term completely in terms of V2. Okay, so that would be nothing but, or in terms of V1 we wish to write, because V1 is given to us, so that would be half rho A, and V1 square you can take common, and V2 can be written as this, so that will be nothing but uh, V2 would be V2 here is A1 by A2. So like V1's or V2 here is, so that would be 1 minus, you can say, that would be A1 square by A2 square simply. So now you must realize that A1 square by A2 square here is a quantity greater than 1. So you must realize the pressure at P2, this term has come out to be negative. This is nothing but a negative quantity over here. So basically we have lowered the pressure over here. That is what our motive was, to decrease the pressure, so that due to the pressure difference, this liquid will be able to rise in this column. So P2 we have got. This is the expression for P2. Now similarly, let's write the equation of Bernoulli's principle in case of liquid. In the previous example also we were able to write that. So let's take 1.4 over here. So you will be able to write like P4 plus rho GH4 plus half rho V4 square is equal to, you can say, P3 plus rho GH3 plus half rho V3 square. Okay, and here at all these points we must take the density of liquid over here only. So first of all, P4 will be nothing but the atmospheric pressure. So this term will become 0. And let's choose this level. Like in the previous one, we already did that. So this level we are choosing it as a reference. Okay. So here, the equation we will be getting, for example, for P3. Okay, and V4 approximately will be equal to 0, like we saw in the previous example. So P3 is nothing but minus rho LGH3 minus half rho L V3 square. And let's approximate this height to be negligible as well. So this term also let's assume it to be equal to 0. So that is going to be simply half minus of half rho L V3 square. So we have got the equation for P2 and we have got the equation for P3. And now you can see that P3 is equal to P2. So that will be giving us, so P3 is minus half rho L V3 square, and let's reverse the sign. So minus half rho A V1 square, and this term will get converted into A1 square by A2 square minus 1 over here, and this minus sign will get cancelled, and this half will get cancelled. So V3 basically, which we are getting it as, that would be rho A by rho L into V1 square into A1 square by A2 square minus 1 root under. And now you have to realize that this term here is constant. So definitely you can say that V3 is directly proportional to root under rho A by rho L. So I hope in the previous year JE paper, you have seen this question already. So once we have got V3 proportionality, the volumetric flow rate of the liquid is simply going to be equal to A3V3. So Q will be directly proportional to root under rho A by rho L as well. Okay, so this was a very famous question, and I chose this problem to discuss over here because most of the students generally are confused regarding this. So I hope I was able to make myself clear while discussing this question. So this was the concept of perfume atomizer, the working principle that comes into play in case of perfume atomizer or a holy pitchkari gun, that is a sprayer you see, that the example we have just studied. Okay, so this is one important concept with regard to JE Advance. Okay, so now let's move on to the another model of problem. Okay, and that again will be related to application of Bernoulli's principle. Okay, so that model of the problem will be um, when the tube or the container is, for example, rotating. So let's look at this example over here. So let's say there is a narrow tube, okay, and here at the end of this tube, although it is closed, and we have made a small orifice of, let's say, area A, and the cross sectional area of this tube is capital A, and we will be working with our regular assumption that capital A would be much greater than small a, and let's say some liquid is filled inside this tube, uh, which is in horizontal plane, and this axis here is in, say, vertical plane over here, or whatever, like the plane does not matter. Let's say everything is in horizontal plane. So let's say this here, this tube is rotating with some angular velocity omega. Okay, so you can imagine that the liquid will come out here, okay, with some efflux velocity with respect to tube, and this, let's say, velocity of efflux is v. We are interested in finding out what would be the value of v again. So we have already looked how to find out the velocity of efflux in a container, okay, which was kept stationary and some orifice was made at some depth from the open surface. We have already looked into that problem, and that is a problem, similar nature of problem. Okay, and we will be applying Bernoulli's principle only in order to solve this question. So let's say the things which are given is the length of this tube L is given to us, and let's say density of the liquid is also given to us, that is rho. Okay, and now we are interested in finding out the value of V as a function of X, where x is the distance of the open surface of the liquid from the axis. So this is x. Okay, so first thing we are looking to find out the velocity of efflux as a function of x. What would this quantity be? And the second part of this question, for example, let's say initially at t is equal to 0, let's say if the value of x was equal to L by 2, means this tube was half filled. Okay, like how much time it will take to empty the tube. These nature of questions we have already gone through, and what we need to do we already know. So with a little bit of modification, will we be able to apply Bernoulli's principle in this case as well? Let's investigate this situation. So now let's see. Let's say one point is here, Okay, let's say this is point 1, and let's take one another point 2, which is just inside the orifice, and let's say another point 3, which is just outside the orifice. Okay, so now you see, when we are moving from point 1 to point 2, now you must realize, due to the rotation of this tube, okay, this cross section will be moving very slowly. So this cross sectional area and this cross sectional area are same, so the kinetic energy per unit volume will not be going to change. So but what is happening over here is, see, once we move from here to here, obviously you know from the discussion of previous classes that the pressure at 2 is greater than pressure at 1. Okay, so at pressure at 2 is greater than pressure at 1 means the pressure energy at point 2 is greater than at point 1. Okay, so what would be the pressure at 2 and what would be the pressure at 1? So you can simply say, like, since this point is exposed to atmosphere, okay, so the pressure at this point, the gauge pressure, is going to be equal to 0. So P1 is going to be equal to 0. So now we are interested in finding out P2. So from here to here, P2 minus P1, we have already learnt this relationship previously, and that is going to be equal to half rho omega square. That would be x2 square minus x1 square, you can say. So x2 is at the end of this tube. So x2 is nothing but L square, you can say, and x1 you can say is nothing but simply x square. So that is P2 minus P1, and P1 is basically equal to 0. So we have found out the pressure at point 2. So that is P2 is equal to half rho omega square L square minus x square, and please do understand this is gauge pressure at point 2. And now when point from point 2 to point 3, what is happening over here? Okay, at point 3 the pressure is suddenly getting dropped to atmospheric pressure. That means the gauge pressure will suddenly become 0. So all of this pressure energy will get converted into the kinetic energy. So this term you can equate with nothing but the kinetic energy per unit volume term. So that would be equal to half rho v square over here. That would be half rho v square over here. Okay, so like this v here is nothing but we are writing in the frame of reference of the tube, the rotating tube here. So v will be equal to, just by rearranging you can see that v will be equal to nothing but omega square into root or omega, it will be taken root, so omega into root under L square minus x square. So that is what the value of v as a function of x we have got. So first part of this question we are already done with. Now second part of the question, okay, like it is asking for us to find out the time of emptying. So you must remember the discussion when we find out the time taken to empty the tank. Same thing we are going to do over here. So we are going to apply to these two cross sections the principle of continuity. So obviously that would be equal to A1 V1 is equal to A2 V2 over here. So A1 we have written it as A already, okay, and V1, okay, the V1 is nothing but the velocity of this cross section. Okay, so v1 is nothing but rate of change of x. Okay, so that is v1 will be equal to nothing but dx by dt. So here we can write a times dx by dt is equal to a2. A2 is the area of cross section of orifice, so that is going to be equal to a into v2. We have already found out that is nothing but omega root under L square minus omega square. So we have got a differential equation in x and t, and now let's solve it. So this is going to be equal to can say that would be dx divided by root under L square minus x square, and that would be equal to a omega by capital A into dt, and we need to integrate both sides. Okay, and let's say at t is equal to 0, the value of x that is given in this question is equal to L by 2, and we want to find out the time of emptying, so let's say that is t. So when the tube will become empty, the value of x will become equal to L. Okay, so this differential equation we need to solve. So obviously we know the integration of this part, so that is nothing but sine inverse, that is x by L. Okay, and limits are, that is nothing but from L by 2 to L, and the right hand side would be nothing but a omega by capital omega into t. So let's solve this. So this will be sine inverse 1 minus sine inverse 1 by 2. Okay, and that would be a omega by capital A into t. So obviously sine inverse 1 is nothing but pi by 2, you can say, and sine inverse 1 by 2 is nothing but pi by 6. Okay, so a omega by a into t, and just t you will be getting, this quantity would be nothing but pi by 3. So you can say that would be pi by 3 omega into capital A by small a. This would be the time of emptying in this case. Okay, so this was one another example. One more example we are going to take over here, like since we have entered into a rotating case of rotating container. Okay, so let's take one more example. So this example is, say we have a cylindrical tank. We have a cylindrical tank over here, which is completely filled with a liquid of density rho. This is completely filled with a liquid of density rho. Okay, and about the dimension of this container, let's say its radius is a and its height is a as well. Okay, and let's say this whole container is rotating with angular velocity omega, and omega is given to us as root under 2g by a. Okay, and it is also given to us that like minimum gauge pressure, you can say, the minimum pressure inside the container is P naught. Okay, so what we are required to find out, the first part of it is like find pressure energy E of liquid inside the container. How much pressure energy is stored within liquid inside the container? That is the first part. And the second part we are looking at, let's say for example, we have made a small orifice here at this point. So from this point, what will be initial efflux velocity? Okay, initial, because see the level will go down, so definitely efflux velocity will change. So we are interested in finding out the efflux velocity initially at t is equal to 0. So how are we going to approach this problem? So first part of the problem is regarding finding out the pressure energy E. Okay, so how are we going to find out? So pressure energy per unit volume, we have already realized pressure energy per unit volume is a P. Okay, so you can say, like, let's use some other color pen. So DE will be nothing but P dV. Okay, DE like energy stored, the pressure energy stored in a small elemental volume of dV, where the pressure as P will be given by this expression, because P is nothing but the pressure energy per unit volume. So we are trying to find out the total pressure energy. So now the thing is, the pressure here is varying vertically downward also and radially outward also. So both these things we need to take care of. So for that, what we need to do, we need to take appropriate volume element over which we could integrate. So what we must do here is, first of all, let's take a cylindrical element of, say, radius r, and small increment in r is dr, which would be the thickness of this hollow cylinder. Okay, so first of all, let's choose this volume. Okay, and the secondly, since the pressure is varying also in vertically downward direction also, so at a depth of h, let's say at a depth of h, okay, let's cut a ring from this cylinder. Okay, let's cut a ring from this cylinder, and small increment in h would be this dh. So our volume element is basically a ring of radius r, okay, and thickness or width dr and thickness dh, you can say. So this is our volume element. Okay, so first of all, and it is given in the question also, that the minimum pressure inside the container is P naught. Can we guess that where the pressure would be minimum? Okay, so the pressure increases vertically downward and radially outward as well. So you can very easily guess that this is the point, that is the center at the top. Okay, this is the point where we will be having the minimum pressure. So if the pressure here is P naught, okay, so can we write the pressure uh, throughout this elemental volume? So when we will be writing this dE over here, P will simply turn out to be pressure at the center. Simply you can write that would be equal to P naught plus rho GH. Okay, and as you move radially outward now to reach here, the pressure will increase by half rho omega square into uh, r square, you can say. Okay, so this is the pressure. And what about the volume? So the volume here will be simply, the volume of this ring would be nothing but, you can say that would be 2 pi r dr into dh. Now you must realize this expression for d, which we have written, has two variables, r as well as h, and both these variables are independent variable, you must see. Okay, and when you will be substituting the value of omega square over here, omega square is nothing but 2g by a, so 2 and 2 will get cancelled. Okay, so what we will be getting over here is, or let's say we will substitute it later, the later stage. So this is the expression for dE. So when we will be looking to find out the total stored energy E, and that will be equal to, we need to do double integration, so that would be P naught plus rho GH plus half rho omega square r square into 2 pi r dr into dh over here. And you need to you need to use double integration. And let's say first of all, from h is equal to 0 to h is equal to a you put, and secondly r is equal to 0 to r is equal to a you put. So this is double integration, although it looks very complicated, but it is easy to solve. So first of all, you need to integrate it with respect to h, and after that you need to integrate it with respect to a. Okay, so let's do it step by step. Okay, so let's leave that integration part, and let's integrate it with respect to h first. And the after putting the limit also, you will be getting 2 pi r dr term will be as it is. It will be acting like a constant. And when you will be integrating this term, p naught plus rho gh plus half rho omega square r square into dh, okay, you will be getting over here is p naught a plus rho g, and h here is also that will become a square by 2, and plus you will be getting rho g, um, you will be getting that is omega square by uh, omega square. Let's value substitute. So after substituting the value, you will be simply getting this term as rho g r square. Okay, so you will be left up with this. So now when you will be integrating this term over here and substituting the limit, and let's take 2 pi common over here, so what you will be getting is nothing but this is p naught a, and r dr integration would be a square by 2 after putting limits, and that would be rho g a square by 2 into a square by 2 again, and this term will become rho g, and the integration of r cube dr would be nothing but a to the power 4 by 4. Okay, so we have already calculated everything, and after rearranging this, you will be getting a cube you can take common, and 2 will get cancelled throughout. Okay, and you will be left up with this p naught plus rho ga. So this is the total pressure energy stored inside this container, and finding out the efflux velocity is, I think, the easier part, because you know the pressure at this point, and that will be pressure energy at this point. So pressure energy will get converted into kinetic energy. So we will be having a very simple expression. So that would be simply, here the pressure is um, now the pressure here would be P naught plus you can say that would be rho GA plus half rho omega square, that is 2G by A into A square. Okay, and that will be equal to half rho V square plus P ATM, you can say. So this term and this term will get cancelled. So ultimately what you are getting, I'm not having space, let me write over here. So you will be getting half rho V square is equal to P naught minus P ATM plus that is 2 rho GA. So obviously V you will be able to get from here. Okay, I'm leaving it for you to calculate, write the final expression. So this was one example. So another thing I want to discuss over here, another concept is something called upward thrust experienced by the roof problem, by the roof. Okay, so let's say this is some hut, and there is a roof of cross-sectional area of area A installed over it, and generally when if it is a hut of some poor old man, okay, you realize that this roof is not properly installed. So what happens that when the wind blows above it, let's say with speed v, okay, like this roof flies away from the house or hut. Okay, so what causes this roof to fly away? As the wind is blowing horizontally, what causes the roof to fly away in upward direction? So we want to investigate this situation. Now the idea is, since the wind is blowing, the wind has started blowing, so the kinetic energy of the air element per unit volume here at the top of roof has increased. So at the cost of which the pressure would be decreasing. So let's say at this point, if we are writing the pressure would be the atmospheric pressure will decrease by half rho v square, and the pressure inside the house is still p atm. So now you can see, let's say if this is point 1 and this is point 2, so p1 is definitely greater than p2. So that will due to this pressure difference, this roof will experience an upward force F, and the magnitude of this force here would be nothing but P1 minus P2 times the area of the roof. And P1 minus P2 is definitely, that is nothing but half rho V square into A. So that is the expression for force that the roof of this hut will experience. And that is very, very important expression. Just you can remember this formula, half rho A V square. Okay. So you remember that formula when we had like ingoing liquid or outcoming liquid used to experience a thrust force that was equal to rho a v square. Now the expression for force here is a half rho a v square. So please try to understand the difference between these two situations and don't get confused when you remember the formula and when to use the expression rho a v square and when to use half rho a v square. So this will be the force as experienced by the roof over here. Okay. And one simple question we are going to do is simply, let's say for example, this is a thin glass plate of cross sectional area A, okay, and it is hinged at this point, okay, and this is a vertical plane, so this is G is in this direction, okay. So the question is the speed with which the air should be blown parallel to its upper surface. What should be the value of this V such that the plate remains horizontal? Okay, so in order to do that, since we are having a hinge over here, what we need to do, we need to balance the torque. So for that we need to find out what all forces will be acting on that. So the force here would be first of all mg, and the force caused by this moving air above it, we have already found that out. So that is nothing but half rho a v square. So obviously the point of application of both these forces is same, that is at the center of mass of this body. So you can say that will be equal to half rho a v square is equal to mg, and just by rearranging you will be able to get the required value of v over here. So now you see like the forces the torques are balanced, and now you see the torque balance equation, or basically here I have written the force balance equation because the arm, the point of application is same for both. So the torque balance equation and the force balance equation are one and same. So here you can say like what would be the force exerted by this hinge on this glass plate over here. So like the force exerted by the hinge will be equal to 0. So before we end this session, let's talk about one more interesting phenomena of the swing balling. Okay, and the swing balling can be explained with the help of a theory that is known as Magnus effect. Let's look into the Magnus effect, which is experienced by a spinning ball. Okay, so now you see, for example, if a ball is moving with certain velocity in air, okay, without spinning, so what will happen? See, there would be air. So in the frame of reference of the ball, the air will look like moving in opposite direction to the motion of ball. Okay, in the frame of ball, imagining the air to be stationary. Okay, so in the frame of ball, the velocity of air will be opposite of the velocity of the ball over here. So this is when the ball is not spinning. That is the first case. And the second case, let's take Okay, so in that case, the velocity of the point above and the below, let's say this is point A and this is point B, so PA will be equal to PB, neglecting the difference of height between these 2 points. So this will not experience any Magnus effect, no dynamic lift, etc. over here. So this will follow its normal trajectory, and this ball will only be moving under the influence of gravity. But now you think, if this ball is spinning, okay, we will be dealing with two specific situation. Okay, like if this ball is moving in this direction and this is spinning in this direction, now you must realize, so if the air whose flow with respect to ball is in this direction, okay, now you realize, so see, due to the drag of this air at this point over here, the air element in contact with this point, due to the drag of this air, the velocity of this point will be increasing. Let's say this is point B, so VB will increase, whereas the this point on the ball is moving in this direction and the air element is moving in backward direction, this direction over here. So this drag of the ball will decrease the velocity of air element at this point. So this VA, so clearly you can see that the VB is greater than VA. So that means PB would be less than PA over here. So that means the pressure at the top will be greater and the pressure at the bottom will be smaller. So this ball will experience a net downward force over here, a downward force it will experience apart from gravity. So it will not be following its normal trajectory, like it will, its trajectory will be lower than that of normal trajectory. Okay, so like the if a swing bowler is there and he is bowling towards a batsman, okay, and the batsman is prepared to have a and he is ready for the normal trajectory, and the ball is swinging and it deviates from the normal trajectory, it will be very difficult for the batsman to predict the movement of ball, and his chances of getting out will be more. Okay, so this was one situation. Another situation we can have, the third situation, you can say, let's say the ball is moving in this direction and is spinning in this direction over here. So the movement of air, like we said, that will be like this. And now see, due to drag at this point, the velocity of ball is in this direction. So this point here, this element of the air will be dragged more, so its velocity VA will increase. And at this point, the velocity of the ball is in this direction, so it will drag the air in backward direction, so it will decrease the speed over here. So VA is greater than VB. So you can say the PA and PB. So PA is this time greater than PB over here. Okay, so the force this time will be in upward direction. And now you must also realize, you must have seen bowlers or some other fielders, or in the fielding team you might have seen the bowler rubbing uh, the surface of the ball, okay, and trying to make the ball rough. They try to make the ball rough over here. Okay, so like if the roughness of the ball is increased, so it will drag the air more, so it will create more pressure difference. Okay, and the Magnus effect will be more in such case scenarios. Okay, so the swing bowling is an art, you can see, and we here have only seen two specific cases. Okay, like if the angular velocity is either in clockwise sense or anti-clockwise sense. So in these situation, V and omega are perpendicular to each other, and now it is up to the intelligence of the bowler in order to manipulate the angular velocity. He can manipulate the direction of an angular velocity, etc., in order to achieve different kind of swing in the swing bowling over here. So like this basically is an art, you see. Okay, so here this week we have tried to cover little all the aspects of fluid mechanics you see. Okay, and a few problems we were also able to deal with. Okay, so obviously there the number of problems you can have more. In order to practice, you can follow many books, you can solve previous year JE problems also. And regarding this chapter, what I have to say is this chapter is very important in perspect to JE. Okay, and easy questions are basically asked, means if you understand the concept fully well, okay, there will be no question you will not be able to solve in the exam. And here I am concluding this section, like this session is over. Okay, and the next week we will be covering some other topic, and here let's thank each other for joining each other. Okay, and let's end the event. Thank you very